Hello, everybody, and welcome to your 24th lecture in Cenozoic life history. This is for your geologic history class, so welcome all. We're just on our basically second to last lecture here, so next time we're just going to talk about humans, where humans came from, and then we'll be all done with the class. So, and I'll just be getting ready for the final, which, by the way, is coming up, and it's very, very difficult. You got to start studying for this thing right away. A few, I wouldn't say a few minutes, but maybe 15, 20 minutes every day is going to do you a lot more good than 3, 4, 5 hours cramming the night before. So you want to be prepared for that. That means taking the practice exam. So some things you should really consider doing is, first of all, take the practice exam. That's number one. Number two is maybe, this is something, whoops, doesn't need an E there. Another thing I really recommend doing is make flashcards, okay? Even if you make the flashcards and you don't study off of them, that really helps too. I'm going to release pretty soon a study guide. In fact, it might, by the time you're watching this, probably be already out. So definitely do the study guide. That's one of the first priorities. But you should start studying now for that because it's a doozy and it's worth, like 25% of your grades. So you need to do well on it. With that said, just continue along here with your second to last lecture on Cenozoic life. So some things that you should take a look here now. The world is obviously changing. Okay, we're going to compare some pictures of the Mesozoic with the Cenozoic a little bit later, but you can see how it's starting to look different. So here we are in the Cenozoic era. Last era, the Phanerozoic Eon, Cenozoic era. And we have three periods, the Paleogene, the Neogene, the Quaternary. The Quaternary only started about, this is 1.6 million years ago. Okay, so the vast majority of this time has actually been in the Paleogene and the Neogene. Okay, so the epochs, you do need to know the epochs of the Cenozoic. So those go Paleocene. That's kind of easy to remember because paleo means old. So Paleocene is the first epoch, right, of the oldest epoch. Then it's Eocene and Oligocene. Okay, so those are the three of the Paleogene. Okay, so Paleocene, Eocene, Oligocene. Next is, for the Neogene, the Miocene and the Pliocene. And then after the Pliocene, it's the Pleistocene and the Holocene. Holocene is today. It's only started 11,000 years ago, 12,000 years ago. Pleistocene started 1.6 million years ago, and that's basically the time of the ice ages. Okay, so those are the ice ages. So anyway, that's kind of our outlook for today. There you go. Paleocene, Eocene, Oligocene, Miocene, Pliocene, Pleistocene, Holocene. Okay, so that's how it goes. So what do you notice different about these two pictures? Here's the Mesozoic down here. Here's the Cenozoic. What is different? So for one thing, you'll notice right away is that instead of having these lush rainforest type jungles, we're looking more at like grasslands and little temperate forests, okay? And that's because, generally speaking, the climate during the Cenozoic has been getting cooler and drier. Now, that doesn't mean it was cool and dry the whole time, but it has been generally getting cooler and drier since the Mesozoic is really a time of like very high heat, very high sea levels, very humid, lots of water, very lush. It's also very high greenhouse gases. Greenhouse gases, like you think we have high greenhouse gases, like high CO2 right now. We had CO2 levels back then that were like 10 times larger. Okay, so it was like a hothouse, greenhouse in the Mesozoic. So things are going to get cooler, going to get drier, more temperate. Also, you see we have mammals being dominant instead of reptiles. So reptiles are going to reptiles, obviously, they're still around, but they're going to fall by the wayside and to make room for the mammals and birds. Birds are also a big deal now, too. So the last thing is, this is obviously climate is changing now, right? So you got relatively cold and dry versus warm and humid climate. So recall that the Mesozoic ended with our massive meteorite impact 65 million years ago. Ended the era of the dinosaurs. It also brought massive changes to life in the oceans as well. So this led to the extinction of non-avian dinosaurs, not just non-avian dinosaurs, but a lot of marine species as well. So you can see this is the KT mass extinction. Again, this is showing how many different species there are, and you see this sudden crash in the number of species during the KT, between the Cretaceous and the Paleogene KT mass extinction. Okay, so this is the diversity of different families of marine families over time. Okay, so we have, this is actually, by the way, just a really good graph to use to study, because it lays out a lot of, I mean, we've talked about all this stuff. We've talked about trilobites, brachiopods, graptolites, bryozoans, tabulate corals, brachiopods, trilobites, jawless fish. I guess we had never mentioned fusulinids, right? And we did mention acanthodians, which are a jawed fish. And crinoids we talked about. We talked about rugose, brachiopods, gastropods, ammonites, all the marine reptiles, right? We've mentioned all this as diatoms, rudous bivalves. So this is a really good, just a really good like summary page. I'd really recommend that you spend some time just kind of looking at this. But anyway, what this is showing is the kind of like number of different marine species over time, right? So we're gonna look right here at the Triassic, Jurassic, Cretaceous. There's the Mesozoic, and you see this crash in the number of species right here, right? So there's a trough. Nothing really compared to the trough of that was brought by the PT mass extinction, right? So that was a massive, massive change. So you're going to start to see marine reptiles are going to die out, ammonites are going to die out. A lot of our types of, now we still have diatoms, definitely, but they took a hard hit and re-diversified. So we'll talk a little bit about that later. Rudists totally die out. There are no more rudists left. Okay, so marine reptiles like mosasaurs, plesiosaurs, ichthyosaurs all died out. They were replaced by things like, sea turtles and saltwater crocodiles and things like that. So some of the theories about like why did these marine, because when you think about it, like it's weird, right? Like why did these marine reptiles do so well and these marine reptiles did not do so well? Well, one of the reasons we think is that with the sun blocked out, we had from the meteorite, massive meteorite collision, threw all this dust up into the air. It blocked out the sun for a long time. It caused a lower amount of solar radiation to be received, long winters, and kind of like warm-blooded animals had a hard time dealing with it, and maybe cold-blooded animals survived a little bit better. We don't know. It's just a hypothesis, and it doesn't 100% make sense because obviously mammals survive; they're warm-blooded. But it does seem, for whatever reason, that probably warm-blooded, like these were probably warm-blooded reptiles. Okay, so it seems like cold-blooded, like the older cold-blooded reptiles, did better. We don't exactly know why. But ammonites, which were king of the world, king of the seas for a long time in the Mesozoic, died off completely. As you know, we don't have ammonites anymore in our oceans. We do have nautilus, we have cuttlefish, we have squids, we have octopus. All of these are cephalopods. Cephalopods. These are all cephalopods, part of the phylum Mollusca. Okay. But we do have these things around. They're dominant now. Ammonites are out of the game. Okay. Diatoms. So the various groups of phytoplankton. Remember we talked about phytoplankton, foraminifera, coccolithophores, diatoms, dinoflagellates. All took a major hit during the KT extinction, left only a few representatives of each family behind. But they bounced back pretty strongly in the Cenozoic, especially diatoms. So Cenozoic was really a time of diatoms kind of taking over the planktonic scene, and created a lot of something that you've probably heard before, diatomaceous earth. Has anyone ever heard of diatomaceous earth? So can't hear your response, but diatomaceous earth comes from the name diatom. So these are types of plankton, phytoplankton. Okay. One cool thing, I think, most of these planktonic things are so small, very, very small. You can't see them. They're just micrometers, very tiny. However, there are some that are actually large enough to see. Now, of course, it makes sense to be tiny if you're going to be plankton, because plankton floats around suspended in the ocean water. If you weigh too much, you're not going to float around in the ocean water. You're going to sink, right? So these are actually benthic forms of foraminifera. So they're in the same protozoan. They're protozoa. They're not animals. They're protozoans. They're in this foraminifera family, and they are large enough to actually pick up and hold and see. So they're benthic. Benthic means existing on the bottom of the ocean, not planktonic. Planktonic means you're floating in the ocean. Okay. So looking at Rudis, right? Rudis were king of the I can't say coral reefs, but king of the reefs for a long time, and they were wiped out by the KT mass extinction. Totally wiped out. And instead we have coral. So that's why, we usually call them not just reefs, we call them coral reefs this day, because corals really took over the reef scene. So especially popular is the scleractinia type of coral. So you always know scleractinians because they have this radial symmetry in these openings right here. So that means that the septa, so you'll have these usually actually hexagonal these hexagonal openings, kind of like that. So you see here, and that actually house the creature that lives in there, the little zooid, and it has these radial septa that go around that hexagonal structure. So that's really very, very classic morphology of the scleractinian corals. Okay, so coming out of the Mesozoic, angiosperms. So let's talk a little bit about land plants. So angiosperms continue to take over the world. So you can see right here, this is angiosperms right here. And this shows that, angiosperms are around in the Mesozoic, but after the KT mass extinction, they really get fat. This graph shows them really getting fat. They're really taking over. Gymnosperms right here. These are our gymnosperms. You notice that they start to thin out after the KT mass extinction. Ferns basically ferns have been around for a long time. They've been there, they've done that. So they were basically unfazed by the, things like bryophytes. Those are things like mosses. They're basically unfazed. Algae is unfazed, right? Protozoans, really, like protozoans such as, like all the planktonic species I was talking about, you notice were, it's kind of unfazed by this. So anyway, a little bit more about angiosperms, right? These are flowering, fruiting plants. You'll notice that right here, angiosperms are shown in the pink color. Angiosperms were kicking butt, before the KT mass extinction, but after the KT mass extinction, you can see that they just got more popular. So cycads start to really die out. Cycads are type of gymnosperms. Conifers. Conifers kind of weren't too badly affected. Ginkgos right here shown in this beige color. Really, there's actually only one species of ginkgo left. That's Ginkgo biloba that I'm sure you all know. It's a popular medicine, herbal medicine. So anyway, angiosperms, as you probably can guess now, are the dominant group of plants on land. So a little bit more about the climate. It's very important to understand this because you need to understand changes in the climate through the Cenozoic, because that's going to help you to understand the major evolutionary changes that were going on and the major evolutionary trends that we see. So the Cenozoic was a time of protracted climate change. Conditions were becoming cooler and drier. So that means that climate change was going on for a very long time over the course of the Cenozoic. So this is mean annual temperature shown right here. And you can see that around the Paleocene, things were maybe like 25 degrees Celsius, pretty warm. Okay. Right now, the average is maybe something close to 15. Okay. And you can see that things were, like I said, becoming cooler and drier through the Eocene, Oligocene, now into the right? This right here is going to be the Neogene period. Okay, into the Neogene, temperatures continue to cool. It's basically during the Neogene and Miocene, it was pretty close to what conditions and temperatures are now. Then in the Pliocene, you can see things continue to cool until we get to this minimum during the Pleistocene. Things were very, very cold, right? If you can believe this, the mean annual temperature was 0 degrees Celsius, so it was freezing. Okay, so that resulted in a lot of Earth being covered with glaciers. Okay, during this time, right, the Holocene, things are bouncing back, and now we're kind of more. Actually, we're more up here, close to 15 degrees Celsius is the annual mean temperature. Okay, so anyway, a lot of this had to do. We'll talk about some of the causes of this climate change. Basically, it has to do with changes in Earth's orbit and also changes in the orientation of the continents over the surface of the Earth. So, believe it or not, plate tectonics plays a big role in what our climate is. So you might ask the question, like, how the heck do we even know, like, what climate was like back then? That's a really important question because, we want to we think that we're going through a period of intense climate change right now, but we don't really know if we can't really compare it to what has happened on the surface of the Earth through the past, right? So we have to have some kind of idea of, like, did the climate change back, in Earth's history? Was it, did it, how long, how fast did that happen? How long did it take? Et cetera, et cetera, et cetera. We want to know all those questions, the answers to those questions. So how do we know what the climate was like? Well, there's a few ways. I'm going to talk about a couple of the ways. One way is just through fossils. So might interest you to know that the morphology, that means the shape of leaves, depend on what the climate is like. So basically, the colder it is, the more serrated the edges of the leaves become. And the more warm it is, the smoother. So if you go around and you start paying attention to Corpus Christi foliage, the leaves on the trees, you'll notice that a lot of the leaves are pretty smooth edged. It's because it's a pretty warm place here. Now, if you happen to take a trip up to Michigan or somewhere up north where it's colder, I bet you anything you'll notice that more of the leaves are serrated, and that's really, really true. If you can actually observe this pretty well. So another thing that we get, another piece of information that we get, is the tip of the leaf. So these are called drip tips. They exist. The longer they are, the more pronounced they are. It shows how wet the climate was. So we get a kind of I can say, qualitative idea of how hot and dry or wet or humidity and temperature levels during different times in Earth's history. So anyway, that's how it is, so the colder it is, the more toothy the tree leaves appear, the warmer it is, the smoother, okay? These drip tips here indicate the level of humidity. So we can look at fossil leaves all through the Cenozoic, and we can get an idea about how temperatures had changed and how humidity levels changed from those leaf morphology fossils, the morphology of these leaf fossils. So other things that give us hints about plant morphology: aerial roots. Let's see, we already talked about drip tips. The lack of yearly rings, right? So you only get rings in the wood if there's seasonal variation in temperatures. But if there's very little seasonal variation in temperatures or growing conditions, you don't get those rings. The wood cell structure, all these things indicate rather tropical environments. Okay, so those are all things. So if we find, tropical plants growing in, what's now modern day Michigan, that's an indication that there was some big changes in climate over the period of the Cenozoic. Now, another way that we know about climate in the past is through oxygen isotopes. So as you hopefully recall, I really do hope you remember this stuff about isotopes, because it will be on your final exam, definitely. You can bet your life on it. It's going to be on there. So you need to know about isotopes. I hope you remember what an isotope is. Isotope is very simply an atom of the same element that has a different number of neutrons. Okay, remember that all elements, all the atoms of a single element have the same number of protons, but they can have different numbers of neutrons. So anyway, oxygen isotopes refer to different isotopes of the element oxygen. Oxygen always has 8 protons, that's what makes it oxygen, but it can have different numbers of neutrons. So we have oxygen 16 and we have oxygen 18. We do have an oxygen 17 as well, but it doesn't really play into this story, okay? So 16 and 18. 16 is the dominant one. 18 is much less, but it's still around. I can't remember exactly the percentage, but maybe it's something like 1%. So this is the thing, is that actually, I'll just kind of say it like this. The amount of oxygen 18 in the oceans at any given time depends upon the average temperature of the ocean. So I'll explain that a little bit. But basically, what you need to know is that there's a relationship between how much oxygen, the concentration of oxygen 18, and the temperature of the ocean water. Okay, so this is how it works. Oxygen 18 vibrates because it's heavier. You know, oxygen 18 has more neutrons, it's heavier. Because it's heavier, it vibrates more slowly than oxygen 16. And since oxygen 16 vibrates more quickly, oxygen 16 is more likely to go into, evaporate into the air. And when that oxygen 16 is differentiated, there's a term we use in stable isotope chemistry called fractionated. So when that oxygen 16 is fractionated, it is, preferably goes into the clouds, preferably goes into the atmosphere. Someday those clouds will travel over the Antarctic. They will fall as snow, they'll become ice, and they'll get stored on a glacier. So what happens is we get evaporation, we get preferential evaporation of oxygen 16. Oxygen 16 preferentially evaporates, goes into the clouds, becomes isotopically light H2O, goes into the clouds, okay? The isotopically light H2O falls, okay? And if there's no glaciers, it just goes back, runs back into the oceans. But if there are glaciers, like during cold periods of Earth's climate, it gets stored in the glacial ice. So glacial ice is enriched in isotopically light H2O. That means isotopically enriched in oxygen 16. Okay, so we have O16 stored here. Okay, so it gets stored here. That means that the ocean water gets enriched in oxygen. Oops, I made an S instead of a. Enriched in oxygen 18. So when it is, I'll get a blue pen out for this. When it is cold, we get enrichment of the ocean water in oxygen 18. When it's hot, we get no enrichment. Okay, so we get basically less O18. Cold, more O18. Okay, so that's all you really need to understand about this is when it's hot, we get less oxygen 18. When it's cold, we get more oxygen 18. Okay, so there you go. There's, this is showing how the oxygen 18s do not vibrate as quickly as the oxygen 16. So the oxygen 16 goes flying up into the clouds and becomes the H2O that goes into the cloud. Okay, now this is the rub. When clams and cephalopods and gastropods and all the little animals that live in the ocean, when they take ocean water and use it to part of the oxygen there to make their shells, they basically preserve a record of what the oxygen 18 levels of the oceans were at the time they were alive. Okay, so we get a record. This is a record of ocean O18 levels. Okay, which is awesome. I mean, it's really cool. We now have a record of what the oxygen 18 levels were over Earth's history. So that gives us an idea about what temperatures were over Earth's history. Okay, and we can correlate that with the fossil leaves and things like that that are more qualitative, figure out what temperatures and what the environment must have been like throughout Earth's history over the course of the Cenozoic. And what we find, by the way, this graph is a little bit confusing because over on this side, this is now. Okay, this is then. Back then. Okay, so this is old. This is now. It's new over here. Okay, so right now you see that oxygen 18 levels, right, are now I don't exactly know why they do this. They do this sometimes. It's very confusing. Notice how the oxygen 18 is this axis is upside down. So up here is -1, down here is 5. Why do they do that? I don't exactly know. I think the reason that they want to do that is so that it correlates. You're kind of looking more at like temperature. Okay, so as oxygen 18 goes up, it gets colder. Okay, so temperatures are rising here. So we had the mid-Miocene climatic optimum. So it's the highest temperature during the mid-Miocene. Okay, we have an early Eocene maximum as well, or climatic optimum is what they call it. Okay, so anyway, the Antarctic ice sheets formed around here during the Eocene. The northern hemisphere ice sheets formed around here during the Miocene. The northern hemisphere ice sheets are now mostly gone. Okay, but we've had Antarctic ice sheets even in the Eocene when temperatures were very, very warm. Okay, so I'm always kind of skeptical when, well, I mean, I guess we didn't have them here, but right here, and temperatures around here. So this is when we had Antarctic ice sheets. Okay, so anyway, let me erase all this stuff on here. So we have to have temperatures about right here in order to have ice on Antarctica. So just to kind of something, I always kind of think, you should take these things into account when people are talking about what would happen if all the ice melted off of Antarctica. Well, it can happen, of course, but you'll notice that we've had ice in Antarctica for most of the Cenozoic. So probably it won't just disappear like that. But anyway, it's definitely, there's melting there because global temperatures are rising here and there. So anyway, but what's the point I wanted to make? So we had an optimum, we had a maximum here during the Eocene. Okay, and we had another one here during the Miocene. But you'll notice that temperatures basically since the Eocene have been getting cooler and cooler and cooler and drier as well. Okay, so that's been the trend. So dramatic shifts in climate cause dramatic shifts in the ecosystems, right? So you're going to move away from dense, warm, humid jungles in the Paleogene, in the Paleocene, in the Eocene, right? When you have the global maximum temperature. And we're going to start shifting to drier grasslands during this time. So now as we go from the Paleogene into the Neogene, we're going to see that grass is really taking over. Grass does very well in drier climate conditions. Okay, so trees still do well, forests still do well when it's cold, right? There's plenty of cold weather forests, but they have a hard time coping when it's dry. So that's when grasses start to take over, is when it gets dry. So anyway, that's the trends. Cold, things are getting colder and drier. Climate changes caused similar changes in the fauna and the animals, right? Animals had to evolve and adapt to survive in this new, different, drier, colder climate. And we're going to go into all those different kinds of changes. Right now, let's focus on diversification of birds. So birds really exploded onto the scene after dinosaurs went extinct. And actually, birds are now the most diverse and most common land animal today. So it's actually not mammals. We kind of think of this time as the age of mammals, but birds really hold their own as well. So you can see in this graph of biodiversity over time, and when different species of birds, different families of birds originated, that, okay, so there were, here's the Cretaceous. There was some diversifying of birds here, a little bit here, a little bit here. But then notice at the KT mass extinction, right there at the KT, man, things just explode like crazy. I mean, look how many different families of birds came into existence after the KT mass extinction. It's massive, just massive. So we have all these different species. I'm not going to go into all these different families of birds, but they've been remarkably successful. They've filled a number of niches in the ecosystem. They are the most abundant land-dwelling animal, and they are in the land, sea, sky, air. They're everywhere, right? So birds have been a very successful family. Now, in the Cenozoic, large flightless birds were actually the dominant predators. So it wasn't, lions and tigers and bears. It was large flightless birds. So things like this were just huge. They were dominant apex predators during the Paleogene. Okay, so by the Neogene, mammals were starting to hold their own, and they eventually outcompeted large birds. However, large birds, of course we have ostriches, which still do fairly well. And we have things like this elephant bird that were common. Well, I shouldn't say common, but they were found in Madagascar, which is kind of a throwback to these old massive carnivorous birds, but these were eventually hunted into extinction. So they were around not too long ago. They were maybe like a few hundred years ago. They were still around, but they were eventually hunted into extinction by humans. So diversification of mammals. Let's get on to our favorite group of animals here, the mammals, because I assume it's your favorite since you're a mammal. But we want to take a look at, again, this diversification chart, and you'll notice, again, the same story with the birds. Once the dinosaurs went extinct, it opened up all of these opportunities, for mammals to fill those niches that were at one time occupied by dinosaurs. So you can see that mammals, again, at the end of the Cretaceous, just exploded in the number of diversifying events. Okay, so, in the Triassic, there was one diversifying event between marsupials and monotremes, and then, we get the difference between monotremes, marsupials, and placental mammals. And then we start to get a little bit in the Cretaceous. But once we get to the end of the Cretaceous and after the Cretaceous, things just explode. So monotremes and marsupials have always been a relatively small proportion of the mammals. Most of our mammals here are now, and this is the major group of mammals, are the placentals, okay, the placental mammals. So all these different mammals that you see here, everything from armadillos to manatees, elephants, to whatever that is, I'm not really sure. Oh, that's an armadillo. What is this thing? That might be a pangolin or something like that. No, that's a pangolin. I don't know what that is. There's an armadillo. That looks like an armadillo too. What's the difference? I don't know. Shrews, moles, what are those things called? Hedgehogs, right? Bats, hippopotamus, right? All these things, ungulates, porcupines, primates. We're going to talk about these as Sternoptera. All these different things are all placental mammals. Okay, so the only things that are marsupials, well, there are a lot of different marsupials. I'm not going to go over all of them, but the marsupial and monotreme families are relatively small. So the way that placental mammals, they really took over in the Cenozoic, and the way that placental mammals work, in case you don't know, is that the amnion, right? So remember, we're all amniotic, right? We're in an amniotic sac when we're young. Basically, the amnion fuses to the uterus and becomes a placenta, and that allows for the transfer of nutrients and oxygen from the mother to the developing baby. So that's a very successful design. It's proved to be extremely successful for gestating our young. So that's not how monotremes do it. Monotremes, remember, that includes the extant duckbill platypus and the spiny anteater, aka the echidna, lay eggs just like reptiles, and they feed their young with milk from their mammary glands. So they're very strange creatures, right? So those are the monotremes. Marsupials, on the other hand, and this is an adorable picture, but so possums are I think possums are the only North American marsupial. I think I'm correct about that. But anyway, marsupials, they give live birth to their babies in an embryonic state. The little baby, that's like, for example, a baby possum when it's born is like the size of like a pencil eraser, like it's really tiny. And they crawl into the mother's pouch, right? Like a kangaroo. All marsupials have a pouch. They crawl in there, and there are teats in there, and they can suckle milk from the mother inside the pouch. So now Australia is a very special place because it split off from the rest of the continents early in the process of mammal evolution, and therefore placental mammals never caught on there. So as a result, Australia is dominated by marsupials. So vast majority of marsupials live in Australia, right? So you have the kangaroo, the wallaby, the possum, some things I've never heard of before. Patamelon, I never heard of a patamelon. Tasmanian devils like Taz, and tree kangaroos, my gosh, wombats, koalas, right? So all these things, bandicoots, all these things. What's the difference between a possum and a possum? I don't know. But a lot of these things, boy, I've never even heard of before. But it's kind of cool because you get this convergent evolution where you get marsupials filling all these niches that placental mammals currently fill. But they're all marsupial versions of the placental mammals. One thing I just think is funny is this, we'll get later into Pleistocene, like Ice Age megafauna, that were like the time when mammals got like huge, like really, really big. And the same thing happened in Australia. So we actually had wombats that were huge, giant wombats. They were the size of an elephant. Can you believe that? Giant elephant-sized wombats. Isn't that crazy? They were hunted to extinction. People ate them. It's crazy. Crazy world we live in. But anyway, we don't have these guys anymore. Diprotodon. They're extinct now. So anyway, you might remember that mammals split off from reptiles in the late Triassic. All mammals originated from cynodonts. Remember, cyno means dog. Don't means teeth. So these are the dog-toothed early mammals. Unclear if they were actually mammals or if they were reptiles, but you can kind of see. I like this picture because they think maybe they had hair, maybe they didn't. We don't really know. We don't know if they produced milk or not. Those kind of things are not really well preserved in the fossil record. But this is a picture of cynodonts, kind of in the early Triassic, feeding on a dinosaur, right? So the vast majority of mammal evolution took place in the Mesozoic, but then a radical diversification began after the KT mass extinction. So most mammal evolution, the most basic structures, had been in place since the Mesozoic times and even the Triassic times. Okay, so anyway, you can see here the tremendous diversification, like I said, of mammals going through the Cenozoic. So, and it's been going on, right? So it hasn't slowed down. You can see these diversifying events going on in the Miocene and the Pliocene. You can see the advent of the primates and Dermoptera. Dermoptera, dermo means skin, ptera means wing. So these are skin-winged animals. They're very weird. There's not many of them around, but they are, well, I'll show you some slides on this. Also, the last kind of most recent things to evolve are the Proboscidea. Probos, nose, right? Those are the elephants. And the Hyracoidea. And Hyracoidea involved, it's these creatures, probably most of you haven't seen these things before, called the Hyrax. So here's a Dermoptera. Always hard to pronounce some of these things. Again, it's most closely related. You can see that it's split off from the primates, so it's very closely related to the primates. You might think, looking at it, it's a flying squirrel. It's not a flying squirrel, right? Flying squirrels are actually, primates are most closely related to the squirrel family. So we split off from squirrels. Primates split off from squirrels quite a long time ago. But they are pretty closely related to the squirrel family. But anyway, these are not squirrels. They are not primates. They're not monkeys. They're not lemurs. They're in their own family called Dermoptera. This animal, it's extant, still living, is called colugo. I think they're in South America, if I'm not mistaken. But if they're not in South America, they're in the South Pacific. This guy, I just find this guy so funny. So this animal is called, they're adorable, this little guy. They're called a hyrax, okay? Hyrax. So you might look at that and be like, that's a rodent. That's just some kind of rodent. You know, like a, I don't know, a rat or something. It's not a rodent. It's not even closely related to rodents. It's totally different than rodents. So here you go. Hyracoidea. Okay, here it is. It's not, let me go back to this thing. Hyracoidea. Okay. It's, I mean, where's rodents? Rodents, right? So rodents split off, these things split off from rodents, you know, a long time ago, right, in the Cretaceous. So they're not rodents at all. And actually, they are most closely related to elephants. Isn't that crazy? You would never suspect that. But these two guys are pretty close relatives. And the one place where you can really see the similarities is right there. The incisors, okay? So the tusks, you know, that you see in an elephant, they're not the canine, they're elongated teeth, right? They are not the canine teeth. They're the incisors. So those are the tusks. So you can see that hyrax have tusks. They have elongated incisors, not canines. So that's kind of one thing where you can see the similarity between them and how you can see the family resemblance. So anyway, I just find that interesting. So I was showing you that about hyrax. But so, you know, speaking of elephants, most mammals still were and still are quite small. But there are lots of giant mammals today, and there were giant mammals back then that were even more gigantic than what we have today. So here's an elephant, you know, modern day elephant. You can see that it's absolutely dwarfed by this creature, which is called Unitatherium, or Unitatherium, that's how you say it, Unitatherium to the right. So this Unitatherium, it kind of looks like, whenever I see these, I think of like the Lord of the Rings movies and those like giant war elephants. Looks a lot like them. And they were like similarly sized too. These things were just tremendous. I mean, you can see it dwarfs the elephant, right? It dwarfs the elephant. It looks like maybe 4 times the size of an elephant. So these things, well, this is Unitatherium. Indricotherium was similarly sized too. Okay, so you can see these were just huge, huge mammals. Another very important group of mammals that started in the Cenozoic were the ungulates. So the ungulates are a group of animals that are very well adapted to that beautiful grasslands that were taking over during the Cenozoic as conditions became cooler and drier. So these are very well suited to life on the open plains. So these are the ungulates. Just some examples of these things. This was kind of an interesting one because he had these claw-like hooves. They could use to grab trees. So this is Chalicotherium. These are early ones during the Neogene. Lepidopterana and Cryptoceras. So ceras means face. Crypto, I don't know what that must mean, but ceras is face. It must refer though to this horn, very pronounced horn on its face. But so ungulates. Anyway, going back to ungulates, those are early ungulates. But the ungulates are hoofed mammals that are very speedy runners. So that allowed them to escape predation on the open plains. Now, running became a thing. Running became very, very important. In the old days, in the Mesozoic, you know, when we had these very dense, woody forests, the name of the game to escape predation was more hiding, you know, because it's hard to run through a jungle, right? Let's face it. Very difficult to run through a jungle. So you needed to hide. So most of the animals that were trying to escape predation were basing themselves either on, you know, being able to be large enough to fight, or being small enough to hide, or the other way is, well, I guess that's it. But now we're going to focus on running to escape predation. So ungulates are good runners, and what the evolutionary trends are is to get rid of some of these excess toes. So the fewer toes you have, the easier it is to run quickly across an open grassland. Okay, so we're going to see this evolutionary trend from tapirs to rhinoceros to horses of getting fewer and fewer toes. The horse's hoof is really just one big toe. He's just sitting on one toe. Isn't that kind of crazy? The hoof is just like a big, it's just that one big toe. Another adaptation we see with the ungulates, getting them more adapted to those grassy, grassy conditions, are changes in the teeth. So if you look at our tooth, this is kind of how most teeth are, and this is how our teeth are. We have the dentine, the pulp, in the center here. We have a cement here in the root, and then we have the enamel that covers it and protects the dentine. Okay, and then here's the gum line, right? Now what happened is as animals became ungulates, began feeding on the grass. Well, grass might surprise you that grass is very high in silica. Silica, you might recall, is very hard, right? Quartz is full of, basically full of tiny grains of quartz. It's very abrasive. And the grass, it does that to defend itself. It becomes abrasive to defend itself from being eaten, right, by ungulates. So to adapt to that, the ungulates needed to develop a harder cement-covered tooth with a high crown. So you'll notice that the cement comes up and covers the entire tooth now, and the crown gets very, very high. And the reason the crown gets very, very high is so that it can wear down. So what happens with a lot of grazing animals that eat grass is their teeth start out really high and they start to wear down over their lifetime. So looking at the teeth of grazers versus foragers, foragers are things that are eating herbaceous plants, herbs, broadleaf plants. Grazers are eating grass. You'll notice that this is the molar of a grass eater. This is the molar of a grazer. You can see that this is a very strange tooth. Those of you who maybe know something about horses or cows, probably more likely here in South Texas it's cows, you know that this is kind of what their teeth look like, right? So they're grazing teeth. These actually belong to mastodons and mammoths, woolly mammoths, by the way. So a mastodon was a forager, ate herbaceous plants. The mammoth, woolly mammoth, was a grazer. He ate grass. Okay, so you can see what the teeth look like. Another thing that I just think is kind of interesting is that while most ungulates are, you think of them as kind of grass-eating goats, horses, right, herbivores. Not all of them were herbivores. There was actually I guess there are some carnivorous ungulates still, but this was a very large carnivorous ungulate that existed during the Cenozoic. It's now extinct, thank God. These things just look terrifying. So this is Daodon. It's actually related to the entelodonts, the hell pigs is what their actually entelodont means. So they are actually related to the pig family. But these were gigantic, you could see horse-sized, carnivorous, fast runners. To me, very scary looking. But anyway, they're extinct now, so thank God for that. Ungulates are split into two families. So we have the arretodactyls and the perissodactyls. Okay, so there's perissodactyls, there's arretodactyls. It all depends on how many toes you have. So perissodactyls have an odd number of toes, so either 1 or 3. So horses are perissodactyls, rhinoceros is perissodactyl. Arretodactyls have an even number of toes, so things like hippopotamus, pigs, swine, elk, deer, antelope, camels, right, 2 toes. Those are the arretodactyls. So perissodactyls are much more closely related to each other than to arretodactyls. So ungulates share a common ancestor with Proboscidea, the elephant family. So it's kind of funny, like I said, what Proboscidea consists of are elephants, the hyrax, and manatees. Okay, so they are somewhat related to the ungulates, but the perissodactyls, here's the perissodactyl group, right? Rhinoceros, tapirs, horses, and the arretodactyls are hippopotamus, like things like the ruminants, which are like, cows, elk, deer, kind of like all the antelope, things like that, and pigs. Okay, and then also one thing that's kind of a little bit strange is that whales actually evolved from the whole whale family, dolphin family. They evolved from the ungulate family. So some people, not everybody, some people consider them ungulates as well. Okay. Now, what about our carnivores? Where did our carnivores come from? So we have all sorts of different families of carnivores. The felines, bears, hyena, canines, the bear cats, the weasel family, otters, mongoose family. These are weird things. The fossa and the seal families. So where did all these different carnivores come from? They all descended from a Paleocene, Eocene creature called the Miacid. So it was kind of like a weasel, probably most closely related to weasels. So weasels are kind of the most, I would say, ancient of the carnivores. Okay, we split carnivores into two different families. So we have the Feliformia and the Caeniformia. So Caeniformia means canine-like, dog-like, and the Feliformia means cat-like, right? So those are the two different groups. Things like seals, wolves, coyotes, dogs, walrus, the weasels, otters. Those are all the Caeniformia, the dog-like, and the Felineformia is everything else. The cats. All these kind of strange, I don't know what the names of a lot of these groups are, but hyenas. There's a lot of these different, like long-tailed cat-like, like wild cat-like creatures that live in Africa. I'm not really too familiar with, but anyway, kind of going into the Pleistocene now. The Pleistocene was the time of the ice ages. It was a time in Earth's history in which we had dramatically low temperatures. Probably the lowest temperatures that we have had since the times of Snowball Earth, if you can remember that, back in the Proterozoic. So very, very low temperatures, very almost unprecedented for the Earth. So we're kind of coming out of that period now of extremely low temperatures and extreme levels of ice coverage. So in the Pleistocene, temperatures reached a dramatic low. Vast ice sheets covered much of North America. All that water going up, being stored into these land glaciers, dropped the sea level to an all-time low. And Earth has been experiencing 20 of these ice ages during the Pleistocene. So the ice would recede and then melt and recede and then the opposite of recede would be advance. So it would be recede and advance. The glaciers would recede and advance, recede and advance, recede and advance. 20 cycles of this during the Pleistocene, which lasted about 1.6 million years. Okay, so we call these glacial and interglacial periods. Okay, so in the Pleistocene, things got very cold. Much of Earth was covered with ice sheets. So here, this is the KT, mass extinction, the beginning of the Cenozoic. And right here, this is the time of the ice ages. Okay, so you can see that what's going to happen is that we get these glacial and interglacial periods. So interglacial, temperatures drop, glacial, interglacial, glacial, interglacial, and we go through 20 cycles of this over the past 1.6 million years. So this is just interglacial cycles recorded over the last 450,000 years. Okay, so that's what's been going on. Now we are currently in an interglacial period. We've been in an interglacial period for about 14,000 years. Okay, so humans were around during glacial periods. They were around during interglacial periods, right? So we're around obviously in interglacial periods. But humans have always existed either in the Holocene and the Pleistocene. So we're going to see what happens, because it's kind of unclear now if we're going to have another glacial period, because some of the climate change that's been occurring, it's not clear now. Maybe we will, maybe we won't. But what's kind of interesting though is that even if we do go into another ice age, we shouldn't experience another one, even if it naturally experience another one, for about 50,000 years. Okay, so the way that these cycles work, we should get another ice age. We should theoretically get another ice age in about 50,000 years. So the reason that we get these cycles come from something called the Milankovitch cycles. Whoops. So Milankovitch cycles are natural cycles that happen, changes that happen in Earth's orbit. Sometimes Earth gets further away. The orbit of Earth gets more elliptical than circular, so Earth can get further away from the sun. Also, there can be changes in the orientation of our tilt of our axis, so seasons become more pronounced. Right now we're at 23.5 degrees tilt, but sometimes you can get 24.5. That'll make the seasons more pronounced. Okay, we can also get wobbles, which is called precession, in the orientation of our rotation axis. So all these changes in the rotation and our orbit, they bring about either more or less solar radiation, and it can cause these glacial and interglacial periods. The thing is, too, is that when Earth gets covered with a lot of ice like this, sometimes it can kind of get stuck in that orientation. And the reason is that ice is very good at reflecting away sunshine. So the sun's solar rays bounce off the ice and they go back into space. And it's once ice covers the Earth, it can kind of get stuck in that way. You can see some of these glacial periods lasted for a very long time because of the very high albedo. That's a high albedo means reflection of Earth's sunlight away from Earth into outer space. Okay. So anyway, what happened during the Pleistocene is a pretty remarkable evolution of the fauna, the mammal. Well, actually, not just mammals. All the animals, all the major groups of animals went through this similar trend of becoming very large. And the reason they became very large is because when you have to deal with these sudden changes in climate that were going on during the Pleistocene, and these times in which the global average temperature was 0 degrees Celsius, it helps to be big. It just helps to be big because it's easier to retain your heat, and it's easier to deal with changes when you're large. Okay, so you get this trend, evolutionary trend, where a lot of animals were just becoming humongous. So this became the North American megafauna. So we get huge versions of everything that we're used to. The Irish elk, look how big one of those is. Boy, whew. Dwarfs a moose, right? A moose is the biggest member of the antelope family, but this just dwarfs it, right? So Irish elk, there's the giant ground sloth. Look at how big that thing is. I mean, it's the size of an elephant. I showed you that wombat that's the size of an elephant. Glyptodon, which were giant armadillos that were the size of like VW bugs. I mean, just huge. Here's how would you like to run into this guy? Short-faced bear. Look how big that thing is. You don't even come up to his belly button. They're just tremendous, tremendous animals. Okay, so humans, but it's kind of funny because your ancestors were running around with all these guys. Can you believe your great-great-granddad had to fight one of these things? No way. But it's true. These things were hunted. This is actually showing a picture. This is from a South American cave, actually showing people hunting giant ground sloth. Right, so that's pretty cool. You can actually see these pictures people are drawing of hunting these now extinct Pleistocene megafauna. Like I said, it's not only mammals that got huge. Here's Argentavis, which was a giant bird of prey, 24-foot wingspan, just tremendous creature. You probably heard of Megalodon, right? Megalodon got huge. It's actually a shark that was big enough probably to feed on whales. So you've probably seen things like this, like pictures of Megalodon's mouth, right? It's tremendous, tremendously large, way bigger than a great white shark. So what happened to all this megafauna? Well, the last climate change going into a glacial period, probably combined with human hunters, really put an end to this megafauna. So humans were very, very successful at hunting these large creatures, and probably think it had a lot to do with why they went extinct. So next lecture, we'll talk about primates and the origins of humans, and we'll be all done. This, by the way, is Gigantopithecus, which was again, part of the Pleistocene megafauna, gigantic ape. So he's kind of cool. But anyway, went extinct in the Pleistocene as well. So we'll talk about humans and where people came from next time, at least people as animals, where they came from. And then we'll be all done with the glass, right? So I'll talk to you next time. And till then, enjoy your day.